Hello and welcome to the Titus Timeout Podcast. I'm Jenny Abney-Civy and today we're going to discuss chilled beams. I felt this was an appropriate topic since Titus will be releasing our new chilled beam product line this week. Like underfloor and displacement ventilation systems, which I've discussed in previous podcasts, chilled beams also came from Europe where they've been used for quite a while. In the US, they're fairly new but are gaining popularity as well. Chilled beams are basically what they sound like, beams that are chilled by cold water. They use convection to provide cooling into a space. There are two kinds of chilled beams, passive and active chilled beams. Passive chilled beams have no supply air inlet. They use natural convection currents to cool the space, and a separate system is used to provide the ventilation air for the space. Active chilled beams have a supply air inlet for ventilation. So let's look at these two types of beams, starting with the passive beam. So let's look at a passive chilled beam. They're always mounted below the ceiling, and they are essentially a casing around a water coil with openings in the top and bottom for air to pass through. This is our water coil right here. Now warm air in the room will rise to the ceiling. Next it'll pass into the chilled beam, through the water coil, and into the space to provide cooling. As I said, there's no supply air on a passive chilled beam, so you have to have a separate system providing ventilation air to meet your ASHRAE 62.1 requirements. Passive chilled beams are not as common as active chilled beams in the US, so let's move on to active chilled beams. Active chilled beams look a little bit like this. They mount flush with the ceiling. There's a plenum on top with a supply air inlet. And then the water coil is mounted here on the face. There are rows of nozzles along the inside of the plenum to allow air to go from the plenum into the cooling coil section of the unit. So let's look at how this works. Your ventilation air will come in through the inlet and will go through the nozzles and then out slots in the face of the diffuser. This will cause a low pressure zone right in the center of the face of the diffuser, just under the water coil. Warm room air is pulled up over the coil and is cooled down. It is mixed with the ventilation air coming through the nozzles and goes into the space to provide cooling. Chilled beams decouple the sensible and latent loads in a space. You can probably find a dozen good explanations for sensible and latent load online. The engineering toolbox defines it as the sensible cooling load refers to the dry bulb temperature of the building, and the latent cooling load refers to the wet bulb temperature of the building. Think of sensible load referring to the temperature on a thermometer, and latent load referring to the humidity. Like I said, chill beams allow you to decouple the sensible and latent load, so the chill beam itself handles the sensible load in the space. The latent load is typically handled with a dedicated outdoor air system, or a DOAS system. The DOAS system dehumidifies the outside air before it enters the primary air stream. One big benefit to this is that you're using water to handle the space load, and water is a much more efficient way to transfer energy. Water is almost 3,500 times as efficient when it comes to heat transfer compared to air. Think of it like this: if a specific volume of air can transfer this much energy, then the same volume of water can transfer this much energy. Now, it's probably not to scale, but you get the picture. Let's make a little room here. Stated another way, a 1-inch water pipe transports the same heating and cooling capacities as an 18 by 18-inch ductwork. This huge difference means that you can cool the space using piping that's 1 inch versus running larger ductwork throughout the building. This saves on the material cost of the ductwork in the building. It should also cost you less to transport that energy through the 1-inch pipe than the 18 by 18-inch ductwork. In a chilled beam system, you still have to run ductwork for the ventilation air though. But even though there is ductwork, it is much smaller because you only bring in enough air to handle the ventilation requirements, not handle the entire load of the space. The ductwork is more likely to be about 5 or 8 inches coming into the chilled beam supply air inlet. Another benefit of chilled beam systems is that they use warmer supply water temperatures and warmer supply air temperatures than a conventional overhead air distribution system. For instance, the supply air temperature of a chilled beam system would be between 61 to 66 degrees Fahrenheit compared to 50 to 55 degrees in a conventional system. The cold water temperature would be 55 to 64 degrees for a chilled beam compared to 40 to 45 degrees in a conventional system, and the hot water temperatures are 100 to 140 degrees compared to 140 to 180 degrees for a conventional system. This warmer cooling temperature and colder heating temperatures will reduce the energy usage of the building. So that's an overview of how chilled beams work. We'll go into more about using chilled beams in a future podcast. Don't forget to subscribe to our YouTube channel, and thanks for taking the time out with us.